Since time immemorial, a veterinarian could give you a diagnosis for your sick cow.
Here's the problem. Bessie has a case of lactose intolerance. Give her these enzyme pills.
But that same veterinarian couldn't diagnose what troubled the animal buried up on the hill. Today, paleontologists can. Their sophisticated technology reaches back in time, even 70 million years, to tell us not what killed the dinosaurs, we know that, but what everyday ailments they suffered. Had the dinosaurs known what was wrong, maybe they could have done something to improve their lifestyle. I'm Seth Shostak.
I'm Molly Bentley. Welcome to Big Picture Science, produced at the SETI Institute, where researchers investigate the nature and origin of life. On Big Picture Science, we step back to get the wide-angle view on science and technology. And in this episode, these days, we have an impressive array of tools to diagnose what ails us. So it's tempting to grab some of them and become your own doctor. But there may be limitations. For example, genome sequencing holds the secret to our genetic lottery, and now it's quick and affordable. But are you prepared for what you might find when you dig through it? One man shares his story. Also, from self-diagnosis to self-treatment. We don't fully understand how our brains do their thing, but some lay people who want them to do it better are forging ahead with brain stimulation. Their own brains. It's DIY Diagnosis.
Okay, so this guy walks into a doctor's office. Well, no, wait, that setup doesn't work. Okay, there's this guy who's a patient. And as a patient, he's unique. A big guy from an unusual-looking family.
They have these big faces that look like a duck's bill, plant eaters. They're found in all continents around the world.
He's a vegetarian, so I'm pretty sure he's harmless.
It wouldn't chomp down at you, but then again, one of the most dangerous animals in Africa are water buffalo, and they're plant eaters, so I still wouldn't approach this animal.
The duck-billed dinosaur may not be as famous as T-Rex, but he challenged T-Rex's 40-foot length.
And if this were part of a joke setup, I might ask, how do you give a dinosaur a checkup? Answer, very carefully. Luckily, the Dino Doc is in.
I am Dr. Jennifer Renee. I'm a recent graduate from the University of Manchester, and I study injuries and diseases in dinosaurs.
Dr. Ane and her team have taken fragile dinosaur bones and carefully examined them in order to diagnose what ailed this particular duck-billed patient. Turns out he had arthritis in his elbow. Dinosaurs had elbows?
Yeah, it's a forearm just like you and me, so it's their elbow joint.
The specific diagnosis from two bones, the radius and the ulna, was septic arthritis. This painful condition is around today, affecting humans and reptiles and birds, which of course are dinosaurs. But how do you diagnose disease if your patient has been dead for 70 million years? And does he have health insurance? Well, I can answer the first part of that question. You use a computerized tomography scan, or CT scan, like the ones that they give in hospitals.
With this technology, Jennifer Ane says we can learn more about the ailments dinosaurs lived with, and that gives us a more complete picture of the past.
Jennifer, I understand from your research that you've learned that a duck-billed dinosaur had specifically septic arthritis. Now, supposing that this patient had come to see you and had been able to get through the waiting room door, how would the patient have appeared to you?
Well, definitely would have hobbled into the doctor's office, not so much walked. But I kind of picture if someone brought a dog or a cat in that had a lame leg kind of bent off to the side, maybe not be able to bend that forearm much, not be able to put much pressure on it so it can't really walk, maybe walk with a limp.
Well, that's not so good. That's pretty distressing. How would this have affected its lifestyle? I mean, could it survive with this thing?
It must have survived for some time because it tried to heal itself. And reptiles and birds are actually pretty good at healing this kind of thing, and dinosaurs are related to both.
Well, what's interesting to me is the fact that we're not really descended from the dinosaurs. I mean, that isn't a very direct line there, and yet they're suffering a condition that we suffer from. So that must mean that arthritis is something that goes back even farther than the dinosaurs.
Oh, yes. Pretty much bone reacts very similar to different stresses, and so if you've got bones, chances are you could get a variety of different conditions. There are some that if you're a mammal versus a reptile versus a bird, you might get more than others. But in the case of bones, if you live long enough, you have enough wear and tear on your bones, you can get arthritis. And just like anything, it could always get worse. So it can get infected, in this case with septic arthritis. In septic arthritis, what's happened is something's attacked the cartilage, some kind of infection's attacked the cartilage, eaten it away. That causes arthritis. Your bones start rubbing against each other. That could maybe open up your bone a little bit. It could seep into the bone. It could keep going if it's not treated.
I see. And I presume it wasn't treated in this case. I mean, no antibiotics for this guy.
No antibiotics for this guy. Unfortunately, we only have 2 bones from this dinosaur. That's what happens when you look for dinosaurs in New Jersey. So I can't tell how far it spread. But if I was a betting person, I would say that this dinosaur was good at containing the infection to just the elbow.
Okay, you say these dinosaur bones were found in New Jersey, presumably not downtown Trenton. But I wasn't even aware that there had been dinosaurs in New Jersey, but I guess that's naive of me.
Well, actually, vertebrate paleontology, so dinosaur paleontology, started in New Jersey. The very first dinosaur skeleton is from New Jersey, Hadrosaurus falci. It was the first mounted skeleton up on 2 legs. So world famous for kind of the start of paleontology. But then what happened was we found all these neat fossils out west. And out west, different kinds of dinosaurs, much more complete dinosaurs. So instead of just finding a leg here, a head there, we're finding almost a whole skeleton. So New Jersey kind of got pushed aside as far as dinosaur fossils, but they still find them every now and then.
The Jurassic Garden state. Well, you got a couple of bones from this particular duck-billed dino, and something about them didn't look right. I mean, what was it that was the tip-off that you had found something pathological?
Well, it's interesting because a lot of people ask, how do you see something is wrong with a dinosaur bone? And actually, most humans could probably figure it out because our eyes are really good at saying something's wrong. So you look at it and you can tell that just something doesn't look right. In this case, it's missing the elbow. It's just completely worn away. And then on top of that, it has what almost looks like cauliflower growing off of the end.
So it had a strange growth on it. Now, were you able to cut this bone up, or was it too fragile for that?
We were not able to cut this bone up, which is why it took so long for us to finally do our diagnosis. And there was a couple reasons. One, again, dinosaur fossils are so rare from New Jersey, so every single one they find, they want to try to keep intact. The other problem is this particular fossil has something called pyrite disease. So pyrite is fool's gold, and fool's gold has iron in it. And anybody who's ever left any metal outside that has iron knows it rusts. So our fossil is basically rusting and crumbling apart. So if we tried to cut it, there was a good chance that we'd actually start losing pieces left, right, and center. So we really didn't want to slice into this fossil.
So how did you analyze it? I mean, what'd you do?
We used something called micro-CT. So very similar to what you do if you went to the doctor to get a CT scan, except the CT scans we use are mostly used by engineers. They have a much more powerful X-ray. So when you get a CT scan, not as powerful because they don't want to harm you. They just want to make sure you're okay. We need to be able to punch through rock instead of just flesh. So we go to the big guns, get nice high-powered X-ray, very small detail, so we can punch through our fossils, but at the same time be able to see all those tiny little features that really helps us diagnose the dinosaur.
Well, I mean, this is the kind of question I probably ask my own doctor. But how did you know it was septic arthritis, not just arthritis?
That's always a problem when all you have to deal with is bones. So all you can do is you can look at the animals that are alive today. So looking at, again, what vets have looked at for reptiles and birds. You make your list of all the possible conditions it could be, and then you have your checklist. And all you can do is kind of cross off your list until you're left with what's the most likely condition.
Have researchers done diagnosis on other dinosaurs? Have you?
Yes. Paleo Pathology, which is the study of ancient bone diseases and traumas, is actually been around since the 1920s. But it's really kind of picked up since we've had the availability of the micro-CT scanners. So now that they're becoming more readily available, more people can use them, which means more specimens can be analyzed. So who knows, maybe within a couple months, someone else will find some more septic arthritis because now they know that condition exists, they have the tools, and they've gotten to look at the collections.
Well, that brings me to my final question, Jen, which is this. How does this research change our understanding of how the dinosaurs lived? I mean, what do we know about dinosaurs by diagnosing diseases that they suffered, 70 million years ago?
There's a couple of reasons why I love this kind of study. And as far as what this brings to science, when you look at bone is a very interesting tissue. It's the only tissue in your body that doesn't form a scar tissue. So when it's healing, when it's combating diseases, it's doing all the same things it basically was doing when you're developing. So just like when you're a developing baby, which means when you study how these things heal, you really get a look at the physiology of the dinosaur. So kind of how this thing is developing, how it's growing, and that's helping us answer some of those questions about, are they more like crocodiles, are they more like birds, those kind of big evolutionary questions. And then as far as for the general public, the other thing that I really like about these paleopathologies is that they really make it an animal. A lot of people, they see fossils and, they're just bones, or they're just, maybe a data point. And when you start looking at something that had a bad day, you realize, no, this was an animal that was alive 70 million years ago. These were actually animals. They had bad days just like we do. And it really becomes more of a story about a past animal versus, again, just a bunch of bones.
Jennifer Ane, thank you so very much for speaking with us.
Well, thank you very much for inviting me.
Jennifer Ane is a recent graduate from the University of Manchester in the UK. She studies injuries and diseases in dinosaurs.
It was kind of interesting. She said, it's an animal because of this disease. She's right about that. I mean, I have a little bit of arthritis. I can sympathize with this dinosaur, and I never really sympathized with dinosaurs in the past.
Think of all the weight on their bones, though. I mean, they have considerably more weight than you.
Well, somewhat more. Yeah, some of them. The other thing, this was stunning to me, that they had a disease that we have today. I take aspirin for arthritis. These guys had the same problem. Clearly, these things go back hundreds of millions of years, these disabilities. I wonder if the trilobites had the common cold. I mean, it makes me wonder.
Yeah, you sort of imagine these dinosaurs walking around complaining to one another about their achy joints, their sore throat, and I guess in the case for some of them, that would be considerable since they had really, really long necks.
Sounds like a Gary Larson cartoon. What really killed the dinosaurs? It was sore throats.
And I guess having septic arthritis puts the sore in dinosaur.
Oh.
Well, as our tools for identifying disease, even across deep time, have become more sophisticated and high-tech, there's a temptation to become our own doctor. DNA sequencing is a diagnostic tool that also probes deep time. It's promising and impressive, but it is still in its early days.
I like to think about genome sequencing now kind of like astronomy in the 1700s. Astronomers had telescopes. They were discovering new planets. They were making important discoveries. But, these things were a little fuzzy and they would make mistakes and there were things that they couldn't see. We're kind of at that stage now with genome sequencing.
Find out what that gentleman learned from his genes about his health and ancestry and what remained a mystery.
It's DIY Diagnosis on Big Picture Science.
Support for Big Picture Science comes from the Making and Science team at Google. Introducing Science Journal, an app to explore and measure light, sound, acceleration, and other natural phenomena. Do you have a question about your environment or a project you've built? Find the Science Journal app, hands-on activities, and more at g.co/Science Journal app and start investigating.
You might be someone for whom the phrase do-it-yourself conjures up warm feelings about a trip to Home Depot, a sheaf of new putty knives, and an afternoon glazing windows. Your motto, professionals, stand down.
I'll take one more can of putty. Heck, I'm feeling fit. Give me the whole case. I'll glaze all 27 windows this weekend. In fact, even better, I'll rebuild all the cracked panes as well. Give me 800 board feet of wood, 10 pounds of lag bolts, and you better give me all the duct tape on that shelf.
With an abundance of resources at your disposal, it's now easier than ever, not to mention cost-effective, to care for your home DIY style. So the emergence of affordable genome sequencing would suggest that we can adopt a similar approach to our health.
Our DNA is a gold mine of health data. Tucked into it are the codes for diseases we've inherited and those for which we're susceptible. If you learn that your genes reveal an increased risk for cardiovascular disease, for example, you might quit smoking and spend more time at the gym. You're trying to stay one step ahead of biology. Simple.
So it would seem. However, even the 49ers found that their search for gold didn't pan out as they hoped. The genetic testing company 23andMe, for example, found itself in a class action lawsuit for allegedly misleading consumers about how well its genetic testing kits could help them prevent or mitigate disease. So it's still early days when it comes to using the double helix to diagnose with any certainty.
Science writer Carl Zimmer knows that, perhaps more than anyone. For years, he's kind of geeked out writing about genes and genomes in books and for the New York Times. So when the company Illumina sequenced his genome, he asked them to please send him all the raw data directly. He wanted to see firsthand what his genome could tell him about his health and ancestry.
Carl, you obtained your raw genetic data, but, that's not so new, is it? Lots of people have had their genome sequenced. Even a cucumber has been sequenced.
Well, maybe one cucumber has had its genome sequenced, but for individuals to get their genome sequenced and to be able to get their hands on all the raw data from the sequencing, that turns out to be harder than you'd expect.
Why is it harder? Are there no people that can do this? Is it just a technical question, or is it somehow an ethical issue or maybe a monetary issue?
Well, we're kind of going into new uncharted waters where we have the technology to not only sequence little bits of your genome, but to sequence the whole thing. And once you have that data, the question is, what do you do with that? You could look at that data as essentially being a medical test, just as a blood test might tell you if you have high levels of white blood cells or something like that. Getting your genome sequenced could tell you if you have a mutation that makes you prone to, say, some kind of cancer. And if that genome sequence isn't rock solid, if that information isn't 100% reliable, then essentially what a DNA sequencer is doing is giving you unreliable information. And so there's a big debate over how much information consumers should get when they want to get their DNA sequenced.
I see. Now, this is really big data in a sense. Big personal data anyhow. And you wanted to do this because of, the possibility that you may be inclined to certain kinds of diseases, but didn't you really want to know who you are? Who is the real Carl Zimmer?
If I want to know who the real Carl Zimmer is, I'll just look in the mirror. I don't need a genome to understand that. But really, I've been fascinated with genomes as a journalist for like 20 years. It's just been amazing watching scientists get more and more power to sequence DNA. And I know enough about how scientists sequence genomes to know that when they want to study a genome, they want to get all the raw data, and that is actually 70 gigabytes of data. That's what I wanted. Let's use my genome as an opportunity to explore how you study genomes in general.
Okay, but that is a big file. I assume it's a long sequence in general, a long sequence of A's, T's, G's, and C's, these base pair symbols. But we're talking 3 billion letters, and that would be, I don't know, I reckon that's 2 million typed pages. Did they give you a disk or something? How did they send your genome to you?
Yeah, this was not something that was going to show up by email. This actually did show up in regular mail. One day, the UPS guy showed up, and he had a package, and I signed for it, and I opened it up, and there was a little black bag inside, and unzipped it, and inside was an external hard drive. And that had this 70 gigabytes of data on it. It was pretty cool to be able to just hold that in my hand.
But were you psychologically ready to find something that might be, in a way, an unpleasant surprise? Maybe some sort of bad news about some disease you were especially susceptible to?
So before I got my genome sequenced, I talked a lot with my wife about this. Was I ready for it? Was she ready for it? We have 2 kids. Would they be ready for it? I even talked to, my parents and my brother about it because, we all share some genetic information. And everybody was basically okay with it. And me personally, I think that we get a little freaked out about genomes, like there's some sort of super terrifying message hidden in there. Sometimes there are, but Most of the time, there isn't. I mean, if you know that your family history is kind of ordinary, if people are dying at relatively old ages of heart disease or what have you, then you kind of learned a lot about your genome already.
Okay, so yours was, I assume, one of these boring genomes. I mean, the very fact that you're walking around today suggests that your family doesn't have a very high incidence of bad genes. Did you learn anything that was bad or good or what?
Well, I have lots of genes that do elevate my risk for a whole bunch of different diseases, cancers and various other diseases, but they're not huge risks. Actually, they kind of nudge up the risk a little bit. And I also have other mutations, most of which kind of slightly lower my risk for things. So in that regard, I'm not that unusual, and there's nothing really there that would change the way I would live my life. But, I do have a mutation in a particular part of my DNA that acts like a switch, and it has a very strong effect on body weight. So I have 2 copies of this particular mutation in this switch, and that means people with that mutation are usually about 7 pounds heavier than they would be otherwise. So, there's a case where a mutation has a pretty clear-cut impact on us overall. And scientists actually know now, in that case in particular, why. I mean, they know that this switch actually turns fat cells from fat-storing cells to fat-burning cells, and my cells are just kind of stuck over on the fat-storing side, unfortunately. But as scientists find out these mechanisms by which these mutations affect our health, that's going to actually open up all sorts of medical advances, because then you learn how to manipulate those pathways.
Well, you see that coming. I mean, the cost of sequencing a genome has dropped by many orders of magnitude just in the past decade or two, and presumably at some point it becomes no more expensive than a blood test. Everybody gets their genome sequenced, and everybody then gets the news. I assume that's a good thing.
Well, it's a good thing if scientists actually know how to interpret all that information accurately. And we're not really there yet. I mean, when I got my genome sequenced, I took it to different scientists, and they would talk to me about the genome, and sometimes they tell me different things. And the reason for that is because they were introducing errors into the sequencing, or there were errors from the start. So for the most part, I was getting an accurate genome sequence, but in some cases there were mistakes in there. And, that's fine if you are doing research. I like to think about genome sequencing now kind of like astronomy in the 1700s. Astronomers had telescopes. They were discovering new planets. They were making important discoveries. But, these things were a little fuzzy, and they would make mistakes, and there were things that they couldn't see. We're kind of at that stage now with genome sequencing.
I was going to say, I mean, you're kind of caught in this never land where finally we have the ability to make a diagnosis of what you're susceptible to, but we don't quite have the technology to do anything about it. I mean, that's got to be a little frustrating.
Sure. I mean, it would be great if doctors were able to say, like, well, you got this broken switch of your fat cells, so take this pill once a day, and that will switch it the other way. That would be nice, but we're not here yet. What that means is that, I have to maybe be a little more careful about what I eat than somebody who doesn't have this particular mutation. And that's fine. But, I also have other mutations that protect me from diseases quite strongly. And those actually, some of them have actually already led to medical advances. So that's been pretty exciting to discover inside my own genome.
Getting your genome sequence is also a way, of course, to meet your ancestors. You're not the only human to claim a Neanderthal in your lineage, and you have done that, but you might be one of the few who has identified those Neanderthal genes in your genome. What percentage Neanderthal are you, Carl?
I'm at least 2%, and that's roughly typical for Europeans. Basically, all people outside of Africa have a couple percent Neanderthal DNA, and that is because as humans expanded out of Africa, where we first evolved, these early humans encountered Neanderthals. There was at least some interbreeding. We don't know how much. And some of that Neanderthal DNA got into our gene pool, and it's still with us today in billions of people, including me and you.
Yeah, well, they say one of the possible consequences of that Neanderthal DNA is red hair. Do you have red hair?
I don't have red hair, but actually that variant is in Neanderthals, but it was also in early humans as well. It's just a variant that's probably been kicking around for a very, very long time and may have arisen independently a few times. But yeah, there probably were some red-handed Neanderthals, which is cool to think about.
But if somebody says to you, right, they only have a few minutes with you and they say, okay, you did this. So who are you, Carl? I mean, what's your background? What did you learn that you didn't know?
It was really fascinating to discover that not only am I Neanderthal, but I may also have a little bit of DNA from another extinct kind of human known as a Denisovan. They've only been discovered from some DNA found in a little pinky bone, maybe about 100,000 years old, in a cave in Siberia. That's all we know about them. They're sort of a distinct branch of humanity that branched off from our ancestors maybe 600,000 years ago. And they said, yeah, here are all your Neanderthal genes. And by the way, it looks like you might be a little bit Denisovan. So they're not 100% sure about that, but I'd love to really nail that down because it would be just fascinating to know how my ancestors picked up that DNA too.
Carl Zimmer, thank you so very much for speaking with us.
Thank you. It's been a real pleasure.
Carl Zimmer is a science writer, the author of many books. He's a national correspondent for STAT, an online magazine that reports on the frontiers of science and medicine. His weekly column, Matter, appears in the New York Times.
As Carl Zimmer said, there's a great promise for understanding the human genome, but it's still a wild country with few roads.
The same goes for the brain. Although neuroscience has made enormous progress, we're just beginning to crack the code of what goes on in our noggin. We hope to know everything from how to cure neurodegenerative diseases to how to strengthen those axon connections that hold the memory of where you left the car keys.
If only. Research institutions, entire wings of university buildings are now devoted to studying the brain, or mapping its dense forest of neurons, axons, and dendrites. Yes, folks, we're poised to make those little gray cells speak to us.
Only we're not there yet. Still, that's not stopping some people from taking action.
My name is Peter Simpson-Young, and I'm a grad student at the University of Sydney studying neuroscience.
Okay, if I'm feeling sluggish, my pick-me-up of choice is a cup of coffee. Maybe two if my brain is stubbornly lethargic. Peter Simpson-Young also drinks coffee, but when he wants more of a jolt, his routine might be to grab a battery, some wires, and
They'll apply these couple of electrodes to some part of your head and apply usually a low amplitude direct current.
Peter Simpson-Young is not a doctor and he's not in a clinic. He's practicing do-it-yourself brain stimulation at home. It's non-invasive, meaning the soft sponge electrodes go on the outside of the head.
Then the current, in theory at least, will go through your hair and your scalp and then through your brain.
Gotta say, I'm personally always a bit cautious about do-it-yourself brain projects that include the phrase, in theory at least. But basically, there you have it. Cure what ails you with a battery and some wires.
Welcome to the shocking world of TDCS, transcranial direct current stimulation.
So often what people do, they'll apply these big sponge electrodes to the front of their head, to the prefrontal cortex. But then there's other things like a device called the Think, where it's these sticky electrodes that stick on your forehead and the back of your neck that tries to run current through the base of your brain. And there's even now a device called Halo Neuroscience, which is a pair of headphones that run a couple of currents into the top of your head.
You're applying a DC voltage, which is, just what comes out of a battery. But, normally a battery is 1.5 volts. How much DC voltage are you applying here? I mean, it probably isn't 500 volts.
So in one method, using transcranial direct current stimulation, you're running 2 milliamps. Other methods, like the Think device that runs current through your brainstem, you're running a bit more than that. But in all cases, you're running quite a small current.
Okay, so you're running a current through your head. That's what you're doing, and it's a low-voltage source and a low-amperage current. If I did that, do you feel anything? Do you feel a tingle when this happens?
Yeah, it depends what you're doing, of course, but it's certainly the case that your skin feels a bit itchy. It's very common people see TENS machines where you apply a current through your arms, your legs, and it's a bit like that. It feels like a itching or tingling sensation.
I see. So it's a little different than sticking your fingers in a light bulb socket.
Yeah, definitely.
All right.
Yeah.
And what's the effect on you? How long do you do this? Do you do it for a minute, an hour? What do you do?
It depends on what you're trying to do. Some people are doing it for cognitive enhancement, some people are doing it for treatment, and some people are doing it for buying one of these special sorts of devices. So people will use different types of brain simulations for different outcomes.
You mentioned that you're using direct current, but direct current, I mean, by definition, it doesn't change. It's just a steady current. And I'm not quite sure how your brain would react to something that's just sort of steady state. Other than maybe cooking the skin on your scalp. What does it do?
So there's a wide variety of different types of stimulation. With some of them are direct currents, some of them are more complex or alternating currents. With the direct current stimulation, under one electrode, because of the way brain cells are oriented, you get an increase in activity, and the other current, you get a slight decrease in activity. So depending on where you place it, you're going to increase or decrease the function of the cells underneath it. Other techniques like transcranial alternating current stimulation have more complex waveforms to change the dynamics of the brain processing.
Well, clearly something prompted you to try this. Was it just curiosity, or did you have some goal in mind? Did you want to improve your brain functioning? And you thought, this is worth a shot.
Yeah, I guess when I was a kid, I had this device from the pharmacist called a TENS machine, which runs an electrical current through your arms or legs to stimulate nerves. And I used to play around with the settings to make my muscles do weird things or my skin feel strange. And then when I was studying neuroscience, I saw this bizarre research coming out with these various brain stimulation techniques. And I really wanted to experiment with myself. So, I wanted to see if I could achieve certain outcomes, like will it improve my cognitive function? But I think my motivation was mainly the novelty of this new technique.
And how often do you do it? I mean, is this a daily routine?
Certainly not. I mean, on occasion, I've tried to use it every day for a week to see if that had an effect. But, on average, I might do something once every couple of weeks.
All right. But when somebody hears about this, and I'm sure it makes for a very interesting dinner conversation with people you've not met before, you say, I'm wiring electrodes to my brain and hoping to improve things. And undoubtedly, they're going to ask, well, have you? And how do you answer that?
I answer by saying I don't know because I haven't controlled for anything. It's fair to say that whatever the perceived effects are within the range of placebo, right? So if someone feels more awake, it's hard to distinguish between the placebo effect or not. But, there's some evidence to suggest that you might get an improved working memory or cognitive function, or maybe a bit of reduced fatigue.
What about somebody who asks you, hey, look, I've got plenty of 9-volt batteries at home. I use them all the time. I'll just, connect them with a couple of wires to my forehead. Do you say, yeah, try it out? I mean, what do you tell them?
I say it's deceptively difficult to administer TDCS properly. And if you're going to try, then you need to spend a few $100s getting a device which is going to work as it's meant to. A TDCS across your head is not going to give you 2 milliamps, and it's not going to be safe. And there are lots of really dodgy devices online that either don't work or don't work like they're meant to.
Well, Peter Simpson-Young, I want to thank you so very much for speaking with us.
My pleasure.
Peter Simpson-Young is a graduate student at the University of Sydney studying neuroscience. And he's not the only TDCS practitioner.
Which prompted neuroscientists to weigh in publicly on the risks of direct current on the brain. Next.
It's DIY Diagnosis on Big Picture Science.
Big Picture Science is also supported in part by Podiversity. Podiversity offers easy access to ad-free podcasts on Android devices. Your subscription to Podiversity helps support the production of Big Picture Science and your other favorite podcasts. Follow your favorite shows and have new episodes downloaded automatically to your Android device. You can download Podiversity from the link at bigpicturescience.org or at podiversity.com.
The number of people practicing TDCS, transcranial direct current stimulation, is not large, but there are enough of them to prompt neuroscientists to weigh in publicly on the risks.
The journal Annals of Neurology published an open letter early in July 2016 from 4 neuroscientists, and it was signed by another 39 researchers, cautioning that the DIY approach to brain stimulation may backfire. The risks simply aren't known. Peter Simpson-Young has read the letter.
I totally endorse everything that was said in that letter, and I think any home user should take what they say seriously. to be clear, I'm aware of the risks and the benefits, and I'm doing it in a safe way.
And after reading the letter in the Annals of Neurology, neuroethicist Anna Wexler was inspired to pen an op-ed for the New York Times. It appeared within the month. A PhD candidate in the History, Anthropology, Science, Technology, and Society program at MIT, she's been studying the practitioners who are involved in do-it-yourself neural stimulation and says that they are a fascinating example of what happens when closed-door research is appropriated for public use, and she's not necessarily opposed to it. Well, Anna, we just heard from Peter, and he says he does DIY brain stimulation. He's not alone. Who is doing this?
It's kind of a loose-knit community of people who stimulate their own brains with electricity. And there's actually not a lot of data on how many people there are, where they're located. There's really not a lot of good data on the movement as a whole, I would say.
Okay, then so how do you know it's happening?
So there's a forum on reddit.com where people communicate, people who do brain stimulation communicate. There's also at least 12 different kinds of direct-to-consumer TDCS devices. So people are buying devices, and the companies are still in business selling them. So it's definitely going on. And along with a collaborator, I'm actually working on what's going to be the biggest study to date on the community. So we've actually partnered with a lot of these companies to directly survey their user base.
Now, part of your job as a researcher is to maybe locate some of these people, these DIY brain stimulators, and get them to talk to you about their experiences?
Yeah, so I've done qualitative interviews with some of the DIYers, kind of on a one-on-one basis. Also, I've talked to a lot of the manufacturers of TDCS devices, so people who sell them to other people.
Now, these are people who are not doctors in general, not scientists, generally speaking, and they're hooking up their brains to electrical currents in some fashion in order to give their brain a boost. Is that, in a nutshell, what's happening?
Yeah, that's a pretty accurate description.
Now, can you give us an example of how this is set up? You wrote in your New York Times op-ed that some of the devices are essentially nothing more sophisticated than a 9-volt battery attached to 2 wires that are connected to electrodes, and then the electrodes go on the head?
That's pretty accurate. I mean, that's what they look like. There are different models. So some provide like a meter that tells you how much current is going in. Some have auto shut-off mechanisms.
Well, Anna, I had to start my car a couple weeks ago. This doesn't sound any different from that.
It's a little different in that, you weren't putting it on your own head. You're putting it on, putting electricity into your car, jump-starting the battery that way.
Well, recently in the Journal of Neurology, the Annals of Neurology, 4 neuroscientists and then almost 40 additional signatories issued a caution about neural stimulation. What prompted these scientists to write this letter?
Ever since 2013, maybe slightly earlier, scientists have been aware that there has been this group of home users. And I use the term home users instead of do-it-yourself or DIY because some people use the term DIY to refer to the actual building of the device, and some people use the term to refer to the nature of stimulation itself so that it's unguided or unsupervised by someone who's been trained in TDCS. So neuroscientists have been aware of this community for a while, and initially they reacted with alarm when they first started hearing about this. But after, I think now it's been 3-4 years, maybe a little more, since the do-it-yourself brain stimulation community has been doing what they're doing, and they haven't gone away and they haven't disappeared. And I think neuroscientists realized that they had to acknowledge them in some way, and rather than just saying, don't do this, providing some sort of guidance and actually engaging with the community was maybe the better way to move forward.
And did they outline specific risks? Are there risks involved that they were concerned about?
So there's 2 different kinds of risks when you talk about TDCS. So one is the short-term risk, so what we might think of as side effects or very acute things that will happen during stimulation. So they said in the letter that they're not going to focus on that because those are pretty well established. You can get headaches. If you're not careful, you can get burns, there's tingling, that sort of thing. And that happens in laboratory studies of TDCS, and that also happens amongst home users. But in the letter, they focused on the unknown. So stimulation may have lasting effects on brain function. That was one of the things they pointed out. Another one was that when you try to enhance one area, you may be impairing cognition in another area. So they were pointing out the areas where they felt that caution needed to be taken.
But isn't TDCS, or transcranial direct current stimulation, something that neuroscientists have been doing for years? What's the difference between what they're doing and what people have decided to do in their own homes?
Well, neuroscientists, before they carry out a TDCS experiment, they'll have to get it approved by the local institutional review board. So all the experiments on human subjects have to be pre-approved. And generally they stay within certain levels of current. They don't stimulate too much or for too long. But there's no such restrictions when you think about stimulating in your own home. The DIYers or home users can stimulate however long they want and using however much current they want. In my research, I found that they actually do mostly adhere to the current levels used in scientific studies, although sometimes they stimulate for longer than the scientists do.
Can you give us an idea of what the current, I guess it would be the current studies, and also the duration? How many volts can you reach, and how long do you stimulate your brain?
So in scientific studies of TDCS, it varies. Usually the maximum is 2 milliamps. And to give you a comparison, in electroconvulsive therapy, which is enough electricity to actually cause a seizure in the brain, that's on the order of, I believe, 600 to 800 milliamps.
This
really
is
a fraction of the current. This is 2.
Okay.
Yeah. So it's a very small level of current. And that's pretty much the maximum current level. Some people stay at 1 milliamp. Some scientists stay at 1 milliamp. Session duration varies. So often it's 20 minutes. Occasionally people go up to 60 minutes. And these are loose ranges, but just kind of giving you a general idea.
Goodness. I thought it was just a zap and you're done. So you're actually wired to this machine that you've built yourself in many cases, and you're sitting there for 20 minutes to almost an hour as electricity is pulsing through your brain.
Yeah.
Now, well, the scientists who wrote in the Neurology Journal said that they were concerned about the DIY use of these machines. As you said, you've been following a lot of these practitioners online and been talking to them, and you discovered actually that they're pretty responsible people and they're thoughtful people in how they approach this. They're not being reckless. Is that true?
Yeah, actually, when you speak to them, they're, for the most part, not all of them, but really they're quite smart. And I think one of the reasons behind this is that figuring out how to stimulate your own brain requires work. So when you buy one of these devices, or if you make one yourself, all you're getting is really these, essentially, a battery and these 2 electrodes coming out. And you have to figure out what to do with it and what you want to do with it. And so you kind of have to do your homework in order to figure out where to stimulate. There's 2 electrodes that are attached to the battery, and one is the cathode and one is the anode. So current's flowing into one electrode and then presumably going through the brain or through the skull and then out of the other. But the orientation of both of those electrodes on the head is thought to be pretty important. And the specific orientation itself is called a montage. So home users research which montages to use for different things. And one of the things I found interesting is that rather than muddling through scientific papers, they've created these almost menus of enhancement capabilities with diagrams of different montages. So, there'll be kind of an image of the brain with a red and a blue dot on them for the anode and cathode. And that will be, do you want to enhance your math? Here's the montage. Your mathematical abilities, here's the montage for that. So there's sort of a barrier, or it's not just easy to put on and click the on button. Or actually, that's not true. There's one device where it's a wearable device and you could pretty much do that. But for the other devices, you really have to figure out the orientation of the electrodes.
Okay, so now could you give us a profile of one of these practitioners? You don't have to use their real name, but just someone who strikes you, who's stayed in your mind, and why they're doing this and what are the reported benefits?
So, sure, I'll talk about one person. And the first person that came to mind was someone who was sort of on the scene, and by that I mean he was posting videos and was posting very frequently to the Reddit forum, and he was using it for cognitive enhancement. He wanted to see if he could increase his working memory capacity. So he would take these tests that were freely available online, just kind of open source memory test, see how he did. And then once he got to a wall, he would then start stimulating with TDCS and see if that helped him improve his scores.
And what did he find? I mean, the question is, Are there any benefits, and are the only benefits anecdotal?
Yeah, it's completely anecdotal. And people who do this realize that. They're not, they call it anecdata. That's actually what I've heard. They realize that this is just, their own self-reports. They're not making any generalizations about it. And they realize that their limitations. So this guy actually realized that it could have just been the practice effect, which is that if you just take a test a few times, you're going to get better at that same test.
Okay, but what are the anecdotal reports that I was able to do crossword puzzles in half the time, or I could suddenly recall memories since, from age of 3? Anything like that?
I haven't seen much memory recall, but definitely performance gains. So say I was able to juggle faster, I was able to learn a new motor skill faster. I felt like I was in the zone. I got the highest level of performance on this working memory task, things like that.
Well, Anna, is this in keeping with what we understand about the brain? And there's much we don't understand about the brain. But the idea that brain cells, neurons, use chemical and electrical signals to communicate. And so if you give the brain a pulse of electricity, maybe it is giving it a brain jump. I mean, as a hypothesis, does it seem like it would work?
Yeah, and what's interesting is that a lot of home users are basically piggybacking off the scientific studies of TDCS, which break along 2 lines. So one area of study is in clinical populations, which look at the effectiveness of TDCS for things like depression, anxiety, chronic pain. And the other main line of studies is looking at the effects of TDCS for cognitive enhancement and for increases in learning and memory and things like that. And the very basic theory of how TDCS is working is that it's not causing the neurons to fire this level of electricity, but it's basically lowering the firing threshold, so making it easier for neurons to fire. So if you're thinking about memory or thinking about a task, it may be facilitating learning or making it easier to learn.
Have you read any reports of some serious harm that's been done?
Not to my knowledge. I mean, it's overall, when you look at the short-term effects, it's a relatively safe technique. There are reports of burns. The electrodes, if you don't use them right, they can heat up and they can cause burns. And if you're distracted and you're not realizing that the electrode is heating up or you're not using it properly, it can give you a light burn. So I think that's probably the most significant adverse event.
I'm amused at the idea of being distracted. I think if I had electrodes on my head, that's the only thing I'd be thinking about.
Yeah. Well, people say that they get into a flow zone or a flow state. A lot of times that's why they're using TDCS, is to get into this very focused state. Mm-hmm. So maybe they're getting into that state and then not realizing it or not aware that that can happen.
Well, Anna, you're a historian and an anthropologist and a neuroethicist. What has drawn you to DIY practitioners of neural stimulation? What is intriguing you about this group?
Everything. But I think the most intriguing thing, at least what drew me to it at first, is that you really have 2 populations using the same device. 2 populations, meaning you have scientists using this device in the laboratory in very controlled settings. They're trained to use TDCS. They administer it only to other subjects in a very controlled environment. And then you have home users pretty much using the exact same device in completely uncontrolled settings on themselves, and they're sort of self-taught. There's no guidance, no supervision, and that sort of thing. And the conflict between these 2 groups, I think, is what fascinates me the most.
Can you just say one more line about that? Why is that conflict fascinating?
Well, I think underlying the conflict is the question of who gets to control this sort of technology, right? So the scientists are saying, it is a laboratory technology, that's its essence, and it should be used in the laboratory. And DIYers are saying, well, actually, you can't control it. It could be used by anybody. I can go make it in my basement if I wanted to. There's contestations over who actually owns the technology, and how those play out has been really interesting. And just to bring that back to the open letter, that's the first instance where scientists actually communicated directly with this do-it-yourself or home use community.
Well, Anna Wexler, thank you so much for speaking with us.
Thank you for having me.
Anna Wexler is a neuroethicist at MIT and a PhD candidate in its History Anthropology, Science, Technology, and Society program.
So it sounds like in the show what we've heard is that when it comes to the brain and the genome, individuals are boldly going forth to try to use this information before we have a complete understanding of either.
Well, it's true. We have all this DNA data now, but interpreting the data, as Carl Zimmer said, is the problem. We still don't have enough of an understanding to do that. And the same is true with brain stimulation. It reminds me of the 1870s when they finally had, electric power was being developed for everybody. They had machines. They were called patent electric medical machines that would cure cancer and everything else. At least that's what they said. Well, in the end, it may turn out that the real answers are not so simple.
Well, we want to thank the duo who help us produce the show and do so with only a minimum of neural stimulation, Gary Niederhoff and Barbara Vance.
Also, our thanks for financial support to Rena Shulsky-David and Sammy David, and to the William K. Bowes Jr. Foundation. Big Picture Science is produced at the SETI Institute, a nonprofit scientific and education organization whose scientists study the origin and nature of life. And a big thanks also to our listeners.
Your ears have been attuned to the episode DIY Diagnosis. I'm Molly Bentley.
I'm Seth Shostak.
If you'd like to hear more Big Picture Science, well, you'll find lots of episodes in our archive at bigpicturescience.org.
And if you're a podcast listener but you prefer listening to over-the-air radio because you're afraid that those earbuds might be reprogramming your brain, check out the listing on our website of radio stations that carry the program. And if your local station is not on that list, consider letting them know you like the show.
Oh, and if you listen to our show via iTunes, we invite you to leave a review on our iTunes page.
And to reach us directly with your comments, well, throw in some faint praise, and then email it all to bigpicturescience@seti.org.
Glazing these windows is more difficult than I thought. I'm losing focus. I need a boost. I know. I'll just wrap these electrodes from my Tesla coil to my temples. Where's the switch? Okay, on. Ah, that did the trick. When I'm done with this, I'm gonna sequence my own genome.